Look at the equation for the equilibrium reaction between sulfur dioxide, SO2, oxygen, and sulfur trioxide, SO3, in a closed system. It says 2 SO2 gas plus O2 gas reversibly goes to 2 SO3 gas, and it gives us delta H is equal to minus 196 kilojoules per mole. Remember that delta H is the energy change, and because it's given us a negative value, we're saying that the reaction in the forwards direction is exothermic. So negative energy change equals forwards reaction, RxN for short, is exothermic. Another thing that we're going to want to do is just have a quick look at what the number of moles of gas is on the reactants and the product side. So I've got a total of 3 moles of gas on the reactant side and only 2 on the product side. Predict the effect of adding more oxygen to the equilibrium mixture. Well, oxygen is our reactant, and we know by Le Chatelier's principle that if we do something, if we impose a change on our equilibrium, then the equilibrium position is going to shift to oppose that change. So adding more reactant is going to shift the equilibrium towards the products. So the equilibrium shifts towards the products. So they're asking what it's going to do to the equilibrium mixture, which means that the concentration of the products is going to go up, or the yield of the SO3 increases. And this is to remove the added oxygen. Predict the effect of increasing the total pressure on the equilibrium mixture. Well, we've got reactant side, 3 gas moles, and on the product side, 2 gas moles. So the equilibrium is going to shift in the direction that can reduce the pressure. That is going to be in the forwards direction, okay, because there are fewer moles of gas on the product side. So equilibrium shifts towards the products because there are fewer moles of gas, or 3 moles goes to 2 moles. And then predict the effect of increasing the temperature. Well, we've said that if we know the forwards reaction is exothermic, and we also know that when we impose a change on the system, the equilibrium shifts to oppose that change. If we increase the temperature, then the equilibrium is going to shift in the endothermic direction to decrease the temperature again. So that's going to be in the opposite direction towards the reactants. So the equilibrium shifts towards the reactants. As the forward reaction is exothermic, and this opposes the change. Or decrease the temperature again. Sulfur dioxide for this reaction is made by burning sulfur. They've repeated that equation but we are looking at this being the product. Calculate the mass of sulfur needed to make 48 tons of sulfur dioxide. Now, when it says tons, we can literally just substitute grams and then resubstitute the word tons. Give your answer to two significant figures. So I'm going to write out the equation for the reaction. Burning means reacting with oxygen. So I've got sulfur plus O2 is going to make SO2, and the reaction is already balanced. So let's look at the mass, which is in not really grams, but is in grams. So we are making 48 tons of sulfur dioxide, so 48 here. Then we've got the MR. They've given us the relative atomic masses, so SO2 is going to be 32.1 plus 2 times 16.0, which is equal to 64.1. And sulfur is just 32.1. And then we've got the moles. And moles, we just need to say to ourselves over and over, moles is mass over molar mass. Okay, so I'm going to do the mass that I've been given that I need to make, 48, divided by 64.1 grams per mole. And that value is equal to 0.75. Okay. Then I need to do that number multiplied by the molar mass, because the ratio is 1 to 1. So I've got the same number of moles here, 0.75, and mass. We rearrange this equation to make mass the subject, so we get is equal to moles times by MR. So I'm going to do 0.75 times by 32.1, and that value gives me 24 point blah blah blah, but they've asked us for two significant figures, and the number we get is 24.03 something. So that is my final answer to two significant figures. Question 13. Fractional distillation can be used to separate different fractions from crude oil. Figure 1.2 and 1.1 give us some information about the process. Explain how fractional distillation produces the different fractions from crude oil. Use the information in figure 1.1 and 1.2 in your answer. This means we've got to quote data and link it together if possible, which is definitely possible to do with this. We would be able to get 6 marks if we were just asked to do the first part, but we've got to include, in this particular question's case, we've got to include that using the data to get our final marks. Okay, so let's write what we know about fractional distillation, and then let's tie in how this data kind of backs that up. And a good thing to do is to link that data together. So let's just put the boiling points in degrees C and add that to our table where we can. So we're tying together the average number of carbon atoms, because those are the same in both bits of information, and add on the boiling points to our first set of data. So where we've got 3 here, that's about 20 degrees C, which I don't need to include the unit again because it's already in my table heading. For 10, we've got maybe 110 degrees C. For 15, which is 1, 2, 3, 4, 5, yep, there. That's about 225. And this one for 20 carbon atoms is about 307-ish. Okay, you might be able to read it more easily on your graphs on paper. And for the lubricating oil that's got a 35 average number of carbon atoms, that's about 450. Okay, so let's talk about the how fractional distillation works. So we know that we heat our crude oil and we pump it into the fractionating tower, and it's hottest at the bottom and it gets cooler as you go up. And we know that the fractions with the lowest boiling points condense higher up because they have lower boiling points. So as you get further away from that heat source, they're going to start condensing when they get to their boiling point. So if you've got a lower boiling point, you'll get further away from the heat source before you start condensing. We know that the ones with the lower boiling points have an average of fewer carbon atoms in their chains. They're shorter carbon chains. We know that this is related to the fact that they have smaller chains and therefore weaker intermolecular forces. And we know that weaker intermolecular forces require less energy to be broken, which is why they have lower boiling points. If you're ever kind of confused about that and find it difficult to remember, just think about a jewelry box. So if you've got a jewelry box that contains some earrings, okay, like they're the small kind of carbon chain length. If you pick up one earring, you're highly likely to just get that one earring. It doesn't take much energy for you to separate that earring from its other earrings. Okay, if you then have a second section in your jewelry box that's got bracelets in it, you're more likely to have one bracelet tangled up with another, so you've got to put a bit more energy in to get those bracelets to separate out. Finally, if you've got some long chain necklaces in there, if you pick up one necklace, you're much more likely to end up getting that necklace tangled up with a bunch of others, and you've got to put even more energy in to separate them. So stronger intermolecular forces for longer chains. Think about how they get stuck together just like necklaces compared to earrings. All right, so let's write this down. So the column is hottest at the bottom, and gets cooler going up. Alkanes with shorter carbon chains have weaker intermolecular forces. So they need less energy to break the intermolecular forces, which I'm going to abbreviate to IMFs. So they need less energy to break the intermolecular forces, leading to lower boiling points. EG. Now we're going to use the data. LPG has only 3 carbons in the chain on average, and a boiling point of around 20 degrees C, but gas oil, which I'm literally picking because it's the shortest one to write, has an average of 20 carbon atoms and a boiling point of around 307 degrees C. So that's me using the data. Now we just need to say what happens. So we've said that the column is hottest at the bottom and gets cooler. We've said that alkanes with shorter carbon chains have weaker intermolecular forces. As the temperature decreases going up, the molecules with lower boiling points condense at higher points in the column, and this separates the fractions. Okay, so a bit lengthy. I could have turned that into maybe 4 bullet points instead, but I've got all of the information there. I have put it into a logical sequence. So we've got statement, then explanation of some of the detail and linking it to the data, and finally linking the whole thing together to say how these two things work together to cause the separation. Finally, then, another 6-mark question with a little one tacked on the end. Look at the information about 3 elements X, Y, and Z in the periodic table. So we've got the atomic number for each of the elements, their melting points, densities, reaction with water, which I'm just going to add here. There is a word missing, and that in both cases should say hydrogen. The energy needed to remove 1 electron from an atom, the atomic radius, the formula of the chloride, and the action of heat on carbonates of these elements. Student A thinks that elements X, Y, and Z are in the same group of the periodic table. Student B thinks they are in different groups of the periodic table. Analyze and explain the information in the table that supports both student A's and student B's conclusions. Who do you think is correct? And again, it's a 6-mark question. It's a level of response question. So we have got loads and loads of data here that we need to look at. But let's think about what it is they're actually asking before we jump in. It says that they are in the same group. Now, what do we know about elements in the same group? They have the same number of electrons in their outer shell. Okay, that's key. That's what we're looking for evidence of. Student B thinks they're in different groups. So we then need to find data that supports both of those students' conclusions and then come to a conclusion ourselves. Now, looking at the first one, we can see that the atomic number of Y is given to us as 11. If you look at the periodic table, you'll see that that means it's sodium, okay, because that has 11 protons in its nucleus, so that's its atomic number, which means that we're looking at everything having to be in the same group as sodium if A is correct. So therefore, we're looking at group 1. Okay. So because the atomic number of X is less than 11, this would mean that it would be above sodium in the periodic table if it was in the same group. I mean, it would have to be above anyway because sodium is in group 1. Z could be in the same period as sodium, or if it's also in group 1, as student A thinks, then it would have to be below. Okay, so let's see if the data fits. Well, we know that the trend in melting points for the periodic table for group 1 is that the melting points decrease. Okay, so whenever it agrees with A, so if it's consistent with A, I'm going to give it a tick. And if it's with B, I'm going to give that one a tick. So if it's consistent with A, the first bit doesn't really help us, but we do know that the melting points do for group 1 decrease as you go down. Okay. The density, there's no clear trend. It's low, then high, then a bit lower. So that kind of supports student B, okay? Unless we had been given the densities of everything, then it doesn't really help us to say, oh, these are the densities of those elements. So that's not very helpful. So it kind of supports B. Reaction with water, because they all make hydrogen, and we know that they're following the trend that as you go down the group for group 1, it gets more reactive. So you've got reacts quickly, reacts vigorously, reacts explosively. That is consistent with student A's idea. The energy needed to remove 1 electron from an atom, that is decreasing from X to Y to Z. So therefore, it's getting easier to remove an electron. We know that as you go down the periodic table, the reason the reactivity increases is because it gets easier to remove that outer shell electron. So that also supports A. And we also know that the reason that it gets easier is because the atomic radius gets bigger. So let's look at this, 0.134, 0.154. Yep, that is supporting A as well. So it's looking like A is very, very correct at the moment. So chloride will have the formula Cl minus. If all of them have the same formula, that means that they have all formed the singularly charged, so just plus positive ion. That means they've all got 1 electron in their outer shell. Which fits with them all being in the same group, just as we said before. Then the action of heat on carbonates breaks down and makes carbon dioxide, no reaction for Y and Z. That kind of supports student B. Okay. Now, I'm not saying that you have to do this whole table in your, in your exam paper, but it might just help you to get everything laid out correctly. So I think we are saying we agree with student A. So student A is correct because, and then student B, we need to give some evidence for that. It's probably easiest for us to start with student B because logically we'd say evidence to support student B. However, student A has all of this. So student B, let's write in favor of B. The reaction of the carbonates when heated does not show a clear trend and nor does the density or neither does the density data. In favor of A, so let's do the trends first. So the melting point, reactivity, and atomic radius all follow the expected trends for group 1, and Y is sodium. Okay, then the really important bit, the formula of the chloride. shows that X, Y, and Z all form 1+ ions, so they all have 1 electron in their outer shell. So they are likely to all be in group 1. So A is correct. Okay, quite nice. Didn't have to write too much, even though we got given loads of data to analyze. And then finally, write a balanced symbol equation for the reaction of element Y with water. So Y plus H2O is how we're going to start. And we need to learn that group 1 metals form metal hydroxides, which have the formula metal OH, because it's Y plus and OH minus. We need one of each, or you could do the crossover method. There are no numbers there, so it just becomes YOH. And hydrogen, H2. Now, you should hopefully know how to balance this straight away, but just to be on the safe side, let's look at this. So at the moment, we've got 1 Y on each side, 1 oxygen on each side, but we've got 2 hydrogens and then 3 hydrogens. So we can make it an even number of hydrogens on the product side by putting 2 OH, which then means I've got 4, 2, and 2. So now I can put a 2 there, which gives me 4 and 2. And then a 2 in front of the Y gives me a fully balanced equation.